Hello everybody, welcome to the video to make up for the day we missed due to the weather. Today we're going to focus on jointly distributed variables. So let's look at a motivating example. Suppose a fair six-sided die is rolled. Let X indicate the event that an even number is rolled. So 1 if it's even, 0 if it's not. Let Y indicate that a 4, 5, or 6 is rolled. So Y is 1 if the roll is 4, 5, or 6, 0 if it's not. What is the probability X and Y are both 1? Well, if X equals 1, that means that an even number was rolled. If Y equals 1, that means a 4, 5, or a 6 was rolled. So if X and Y are both equal to 1, that means it must have been a 4 or a 6. So in this case, we know that the probability of that would be 2 out of 6, or 1/3. We want the probability X is 0 and Y is 1. Well, if X is 0, that means it was not even, so an odd number was rolled. Y equals 1 still limits us to 4, 5, and 6. So if X is 0 and Y is 1, we must have rolled a 5. Thus, the probability that X is 0 and Y is 1 is 1 out of 6. We can then actually display all probabilities associated with these events. We list the possible values for X and the possible values for Y. X can be 0 or 1. Y can be 0 or 1. We already calculated the probability they're both 1 is 1/3. And the probability that X is 0 and Y is 1 is 1/6. Note that the ones across the top are X, the ones down the side are Y. Now if X is 0 and Y is 0, that means we must have rolled an odd, and it had to be 1, 2, or 3, which leaves us 2 options out of 6, so the probability would be 1/3. If X is 1, then it's even. If Y is 0, then it's 1, 2, or 3. The only possibility is 2, and so our probability is 1/6. Note that if we sum up over all possible values of X and all possible values of Y, the probability of X and Y, we get 1, as we should. We call this table a contingency table. They're defined by a joint probability mass function, f of x, y, which gives the probability that x equals some value x, and y equals some value y. The function must be between 0 and 1 for every pair of x and y. The values must sum up to 1, and the probability that x, y is in some set A is the sum of all x and y in A, f of x, y. So let's look for the probability that x plus y equals 1. Well, again, if we list our values for x and our values for y and calculate x plus y in each case, we would get 0, 1, 1, and 2. Thus, we see that this is equal to the probability that x equals 0 and y equals 1, or x equals 1 and y equals 0. Since these are disjoint events, we can add their probabilities together. Or in terms of the joint mass function, this would be F01 plus F10. And looking at our table up above, we see the probabilities of each of those is 1/6, thus giving us an overall probability of 1/3. We have a theorem. Let's say x and y have joint frequency function f of xy. Then fy, which is the PMF of y, is equal to the sum over all values of x of f of xy. And f of x, or fx, which is the probability mass function of x, we take f of xy and sum over all y. We can also calculate the conditional frequency, f of y given x, as f of xy divided by fx of x. And we can define independence. X and y are independent if and only if f of xy equals fx of x times fy of y. And as said before, all these values must sum up to 1. So let's look back at our table of probabilities for a second. What I'm going to do is put totals at the end of each row and column. One-third plus 1/6 is 1/2. So the total for every row and column is actually 1/2. And notice that if we add the totals, we get 1. Now the question is, what do these 1/2s represent? Well, notice that this is equal to the sum over all values of x of f of x 0, since y is 0 on that row. And this would be the sum over all values of x of f of x 1. This would be the sum over all values of y of f of 0 y. And this would be the sum over all values of y of f of 1 y. So by our theorem above, particularly parts 1 and 2, this would actually be fy of 0. This would be fy of 1. This would be fx of 0. This would be fx of 1. So these give us the individual probabilities that y is equal to 0, or y is equal to 1, or x is equal to 0, or x is equal to 1. The last row gives us the probabilities associated with x, and we call these the marginal probabilities. The last column gives us the marginal probabilities for y. From the table, what is the probability x equals 1? Well, that would be fx1 by definition of the probability mass function. We see that that number is 1/2. And that's how we calculate marginal probabilities. We fix some value of x or leave it as a variable, and then sum f of xy over all possible y to get fx. For fy, we fix some y or leave it as a variable, and sum fxy over all possible x. What if we know that an even number was rolled? How does this change the probability that y equals 1? So we're looking for the probability that y equals 1 given that an even number is rolled, meaning that x has to be equal to 1. So what we're looking here at is then the function, the probability mass function of fy given x at 1, 1. Now by our formula from the theorem, this would be f of 1, 1 divided by fx of 1. Looking at our table, f of 1, 1 is 1/3. And we found that fx of 1 was 1/2, giving us a probability of 2/3. And so again, we have a restatement of our conditional probability formulas. Now let's look at something a little more complicated. In this example, we're given a formula for f of xy. F of xy equals x plus 2y over 18, where x can take on the values 1 and 2, and y can take on the values 1 and 2. And we want to determine the marginal probability masses. First, let's calculate f of x1. This will be the sum over all possible values of y of f of 1, y. So in this case, that'll be f of 1, 0 plus f of 1, 1 plus f of 1, 2. So if x is 1 and y is 1, we get 3/18. If x is 1 and y is 2, we get 5/18, giving us a total probability of 8/18 or 4/9. We calculate fx2, which is the sum over all possible y of f2y, which is f2, 1 plus f2, 2. Plugging in 2 and 2, we get 6/18. Plugging in 2 and 2, we do get 6/18, but first I should plug in 2 and 1 and get 4/18, which gives us a total of 10/18 or 5/9. Note that fx1 plus fx2 equals 1, which is appropriate. Since these are the only possible values for x, their probabilities have to add to 1. Thus, fx is defined as being 4/9 if x equals 1, 5/9 if x equals 2. For fy1, we want to sum over all possible values of x, f of x1. So that would be f of 1, 1 plus f of 2, 1. 1, 1 gives us 3/18. 2, 1 gives us 4/18, giving us a probability of 7/18. We should already know this value by just subtracting 7/18 from 1. Should be 11/18, but let's calculate it anyway. We sum over all possible x, f of x2, which gives us f of 1, 2 plus f of 2, 2. which is 5/18 plus 6/18, which is indeed 11/18. Thus, the probability mass function for y is 7/18 if y equals 1, and 11/18 if y equals 2. Now, to check for independence is a bit more complicated. We say they are independent if f of xy is equal to f of x times f of y for all x and y. This is the same as saying the entry in row M, column N, is equal to the total of row M times the total of column N. So let's find our marginals. 1 plus 2 plus 4 plus 3 gives me 10/30. 2 plus 5, well, I can figure out that this would have to be 2/3 just because they have to add up to 1. Adding up the columns, I get 3/30, so 1/10. 7/30. 8/30, which is 4/15, and 12/30, which is 6/15. Now I notice, for example, that f of 1 is equal to 1/30, which is equal to 1/10. Well, let's write it this way. Yeah, 1/10 times 1/3. Which is equal to fx of 1 times fy of 1. So that one cell it certainly works for. But that's not enough. Does it work for all of them? If we look at f of 1, we see that the entry is 2/30. But fx of 2 is 7/30. And fy of 1 is 1/3. So fx of 2 times fy of 1 is 7/90, which is not equal to 2/30. So f of 1 is not equal to fx of 2 times fy of 1. So x and y are not independent. They are only independent if it holds for every entry on the table. We can also talk about expectation. To calculate the expected value of x, we sum over all x and y, x times f of xy, which is equivalent to the sum over x of x times fx of x. And similarly for y. The expectation of a function of x and y is the sum over all values of x and y of g of xy times f of xy. So for example, the expected value of xy squared would be equal to the sum over all x and y, xy squared f of xy. Now, if x and y are two different random variables, the mean of the sums of the pairs is the same as the sum of the means. And the difference is the same as the difference of the means, which makes life a bit easier. Their variance, if we add them together, the variance is the sum of the variances. And if we subtract them, the variance is the sum, notice, still the sum of the variances. Importantly, the standard deviation of x plus y is not equal to the standard deviation of x plus the standard deviation of y. The standard deviation of x plus y is equal to the square root of the variance of x plus the variance of y. So now let's calculate the expected value of x, the expected value of y, and the expected value of x times y. So it's the same as the last example. We had marginals 1/3, 2/3. One-tenth, 7/30ths, 4/15ths, and 6/15ths. The expected value of x is most easily calculated using the marginals. Possible values of x are 1, 2, 3, and 4, and the marginal probabilities corresponding to those are 1/10, 7/30ths, 4/15ths, and 6/15ths. Now I do not feel like doing this by hand, so let's type this into RStudio. First thing I do is I make a list of the values of x. Then I make a list of the probabilities corresponding to them. And then I want to multiply each value by its probability and add all the results. Do that, and I get a value of 2.9667. I'll do the same for y. The possible values of y are 1 and 2, corresponding to probabilities 1/3 and 2/3. Sorry, that should be a C there. And if I do sum of y times py, I get an expected value of 1.6667. Now the expected value of x times y is a bit more complicated. The expected value of x times y has to be calculated by summing over all possible values of x and y, x times y times f of x, y. Now we could do all this by hand. We can also do it in our studio, but it's a bit more complicated. In fact, it's probably best if we do this row by row. In the first row of our matrix, y is constantly equal to 1. The x values are 1, 2, 3, and 4, and the probability values are 1/30th, 2/30ths, 4/30ths, 3/30ths. So what I'll do is I'll write 1, 2, 4, 3, and then divide the whole list by 30. And this would give me the sum over the first row. I can then use very similar things to add up the second row. In the second row, y takes on a value of 2, x goes through values 1, 2, 3, and 4, and the probabilities are 2, 5, 4, and 9 30ths. And so if I add these two sums together, that should give me the expected value. At least it, wait, did I do that right? Let me double check this real quick. Yes, I've done it correctly. And so we get the expected value is 4.9666. Wow, 667. So in each of these cases, we want to sum up y1 well, ym, where m is the row number, times c of the row values sorry, this is complicated to explain, times one list with all x values times one list with all the row values. And we add these for each row. And that's one way to do it in RStudio. RStudio does deal with matrices, but it's not going to do so well with this. We can also define what's called the covariance of jointly distributed random variables. The covariance of x and y is the expected value of x minus mu x times y minus mu y. Or more simply, the expected value of x times y minus the expected value of x times the expected value of y. And we calculate the correlation coefficient of x and y by taking the covariance of x and y and dividing by the product of their standard deviations. Some quick properties. Order does not matter. The covariance of x and x is simply the variance of x. If x, y, and z are jointly distributed and a and b are constants, then the covariance of x and ay plus bz is a times the covariance of xy plus b times the covariance of xz. The variance of x plus y is the variance of x plus the variance of y plus 2 times the correlation of x and y times the standard deviation of x times the standard deviation of y. Almost similarly for minus, except the last term is subtracted. If x and y are independent, the covariance is 0. And if jointly distributed random variables are pairwise uncorrelated, meaning between any two the correlation is 0, then the variance of their sum is simply the sum of their variances. So all that's a lot. Make sure you go through it. We have here a table, the joint probability table of X being the number of sports someone is involved in and Y being their age. We want to determine the expected value of X. Now here's one place we could use the matrix command in RStudio to save us a little bit of time. So here's what I'm going to do. I'm going to make a matrix with the probability values. The command for this is, well, let's first give it a name. Let's call it P. I use the command matrix, and then I type a list of the values, left to right, top to bottom. So 0.03, 0.09, 0.06, 0.02, 0.015, 0.045, 0.03, 0.01, 0.045, 0.135, 0.09, 0.03, 0.03, 0.09, 0.06, 0.02, 0.03, 0.09, 0.06, 0.02, and then I tell it how many columns there are. This matrix has 4 columns. If I then type P, I get my matrix. I should get it added up to 1, and I do. So at least if I've made errors, I've made them consistently. Now to find the expected value of x, the first thing we want to do is calculate the individual distributions for x. And to do this, I'm going to use a weird function called apply. To matrix P, I apply, is it 1 or 2 here? Let's see, x is the column, so I want to add along the columns. I just had it. Where did it go? Two. And I want to apply sum. And what this will do is sum up the columns of the matrix. What the heck? There we go. And I get my probabilities. My x values were 0, 1, 2, and 3. And so to get the expected value of x, I can simply sum up x times px. 1.525. So this command says add the columns of matrix P. Now I'll do the same thing for Y. The probabilities for Y, I'll apply to matrix P along the rows, the sum command. And I'll get my probabilities for Y. My possible Y values were 14, 15, 16, 17, and 18. One quick way to do this is just write Y is 14 to 18. And then I can sum them up. We get 16.125, which is the expected value of Y. Using matrices, I can then do a slightly shorter way of doing this. So let's see. I said before that I want to do each row value. In this case, the first row value would be 14. Times the entire row, times all the values of X times the entire row. Well, it turns out to do the first row of a matrix, you just type this notation. And this will give you row 1. The first entry is row, the second is column. If you leave it blank, you get the entire row. So for example, doing this along the entire first row, I would get 3.99. How many rows are there? 5 rows. Okay, so I've got to do this 5 times. I just have to change the value for Y on each row and the row number. 16 corresponds to row 3, 17 to row 4, and 18 to row 5. If I then add all of these together, I get the expected value of 19.95. So that is quite a bit shorter. So note, if I type P, M, comma, that will give me row M. Whereas if I typed P, comma, N, that will give me column N. Finally, we're asked to find the covariance of X and Y, which is very easy at this point, because that's simply the expected value of X times Y minus the expected value of X times the expected value of Y. So in this case, we'll have 19.95 minus 16.125 times 1.525. Give me a second. Yes, after double checking, covariance can be negative. That's perfectly fine. Negative 4.6406. And so you can see this is much more difficult to deal with when we're dealing with jointly distributed variables. It's not fun, is it? Okay, I think you've got the idea for now, so I'll post this video and we'll do some additional questions on Tuesday.